Hi, everyone. Today we're going to begin Unit 3, which is called Quantum Theory and Periodicity. Today what we're going to focus on is the quantum theory aspect of this unit. One of the things that we're going to be looking at as we go through this is the relationship between electrons and waves. And to do that, we're going to start by going over a few basic terms that you need to know in order to talk about electrons and how they behave like waves. We're going to start by talking about wavelength. Wavelength, as you can see behind me, is the distance between corresponding points on adjacent waves. So if you notice, I have indicated one wavelength at both of these points. So wavelength is just the distance for one complete cycle. It doesn't have to be from a specific point on the wave. This would also be considered one wavelength from this point here to this point here, where it would cycle through one complete time. The next term that we have to be familiar with is the term frequency, which is simply the number of waves that pass a given point in a specified period of time. And for us, that specified period of time will normally be 1 second. So if you notice, we have two different waves here. This time interval between points like this is going to represent 1 second of time. So the number of waves that pass in 1 second of time can be considered high frequency or low frequency, which is a relative term. So compared to the wave below, this wave up top would be considered high frequency. This one would be considered low frequency because fewer waves pass in the same period of time, in the same time interval of 1 second. The next thing that we're going to talk about is the electromagnetic spectrum. And this is simply a graphic that shows all of the different types of light energy and what their relative wavelengths would be. On the low end, so low in energy, low in frequency, and long wavelength, we'll find radio waves. So radio waves are meters long. So if you notice, they have examples of football field and human. Shorter than radio waves are microwaves, and these are on the order of the size of a bee or the size of a pinhead. What we would consider extremely small, but nowhere near as small as we're going to see later on. When we go to infrared radiation, those are even smaller wavelengths. So infrared might be the energy that your remote control uses to communicate with your television set. Below that, you'll find the visible light portion of the spectrum. So on the low end, we have red light, which is around 400 nanometers, or excuse me, 700 nanometers. And on the shorter end, we have violet light, which is around 400 nanometers. Smaller than violet, we go into ultraviolet, X-rays, and then eventually gamma rays. Down here, we have extremely high energy, we have very high frequency and short wavelengths, as you can see from this picture here. So what are you going to need to take away from this? Here's what I want you to know. First, I want you to know the order of those 7 specific types of energy that we're going to talk about. So those would be radio waves, microwaves, infrared radiation, the visible light portion of the spectrum, including the order, knowing that red light is lower in energy than violet. Then past that, we're going to need to know UV, X-rays, and gamma. In addition, it will be important for you to recognize that radio waves have long wavelength, they are low in energy, and they have low frequency. On the high end, we have short wavelength, high energy, and high frequency. Next, there are two terms that we need to be familiar with. The first one is photon. So a photon is basically a bundle. It's a particle of electromagnetic radiation having no mass and carrying a bundle of light energy, also known as a quantum. The second term that we need to know is ground state. And this is the lowest energy state of an atom. It is where all of the electrons are in their lowest unoccupied energy level, so the lowest possible position in terms of their positions in an atom. And our third term is going to be called excited state, a state in which an atom has a potential energy that is greater than it has in its ground state. This usually occurs when an electron has absorbed energy and has been promoted to a higher energy level in the atom. If you look here, I have three distinct pictures. We're going to start off looking at the picture on the left side. In a ground state, an electron would be in the lowest possible energy level. So if we're looking at the atom hydrogen, hydrogen would have a single electron in its first energy level. Now, if that electron is hit with a photon and absorbs energy, that electron could be promoted to a higher energy level. Let's say the third energy level. So, struck with a photon, that's going to jump up to a higher energy level. We call this the excited state. When there are energy levels that are unoccupied, that are closer to the nucleus, so lower in energy, but yet that electron is traveling out here. This is a very unstable form of an element. And in order to go back to the ground state, that electron will have to release energy. So it might release energy and drop down to the second energy level, where it might release energy and drop all the way down to its original first energy level. Once the electron releases energy and returns to the first energy level, we go back to saying that it's in its ground state. Lowest unoccupied energy level is now where that electron sits. So just showing you again what that would look like on a close-up view. So imagine that these energy levels, so first energy level, second energy level, third energy level, fourth energy level. We have an electron sitting in the first energy level. This is considered to be the ground state. If that electron is hit with a photon, it will jump up to a higher energy level. So it might jump up to the third energy level, or it might jump up to the fourth energy level. Temporarily, if that electron is up here in a higher energy level, we call this the excited state. When that electron releases energy and falls back down to a lower energy level, sometimes that release of energy is accompanied by energy in the visible light portion of the electromagnetic spectrum. If it is, you will see essentially a burst of color. And depending on what atom you have, that color could be made up of several different wavelengths. Eventually, that electron will continue to fall back down until it returns to the ground state. This picture is essentially the exact same thing that was going on the previous slide. Imagine that these lines here were to extend like this, and you would have the same exact circles that we had, or energy levels that we had on the previous slide. So we talked about energy being released in the visible light portion of the spectrum. Here are three different elements: neon, mercury, and sodium. When they release energy, when electrons fall back down, you'll see a pattern that develops that's specific to that atom, almost like a fingerprint would be on a person. So that fingerprint, or that pattern of light energy that's released, could be used to identify the specific atom that you have. If you notice, there are two different types of spectrums. There is an emission spectrum, which is where we would see the light being emitted, but you could also consider an absorption spectrum, which has a complete profile of all colors from 400 nanometers up to 700 nanometers. Remember, longer wavelength. This is lower in energy, the red portion. This is higher in energy, the purple portion, or violet. So here, you'll notice bands where there is no color. That's where that energy has been absorbed. When those electrons go up in energy levels, you'll see this pattern. When they fall back down in energy levels, you'll see an emission spectrum pattern like this. There are two different equations that we will use when we calculate the amounts of energy, the frequency, or the wavelength of these different photons. The first equation, C equals lambda V, or C equals lambda nu, we'll talk about the relationship between the speed of light we're going to say is 3.00 times 10 to the 8th meters per second. We're going to talk about wavelength, which is measured in meters. And finally, we'll talk about frequency, which is measured in either 1/seconds or sometimes referred to as hertz. So frequency could be measured in hertz or 1/seconds. They're synonymous. They mean the same thing. By the way, this is a Greek letter. It's known as lambda. This is the Greek letter nu. There is a second equation that we will use. This equation talks about the energy of the photon. Energy is measured in joules. We have the same nu, the same Greek letter here, which will again represent frequency. Seconds or hertz. And we have another constant called Planck's constant, which is 6.626 times 10 to the negative 34th joules times seconds. When you're working with a constant, that means anytime you see that number, you're going to replace C with this number, or anytime you see H, you're going to replace it with this number. There is a third equation, and the third equation is a combination of each of these. If you notice, the top equation has frequency in it, as well as the bottom. If I were to solve the top equation for frequency, I would get frequency equals speed of light divided by wavelength. What I can do is, now that I have solved for frequency, substitute this equation, speed of light divided by wavelength, in for frequency down here, and we wind up with a new equation. Which says that the energy is equal to Planck's constant times the speed of light divided by wavelength. We will now look at several example problems that show us how to use each of these three equations. The first one, if the speed of light, so remember, speed of light is c, 3.00 times 10 to the 8th meters per second, calculate the wavelength of electromagnetic radiation whose frequency is. So we are looking to calculate wavelength, and we're given the frequency, 7.50 times 10 to the 14th hertz. But remember, hertz is really 1/seconds. We're going to use the following equation. C equals wavelength times frequency. We're going to solve for wavelength. So that means we're going to divide by frequency on both sides. We'll cancel out on the right side. So now I can substitute in my quantities. I have 3.00 times 10 to the 8th meters per second divided by frequency 7.50 times 10 to the 14th 1 over seconds. Typing this into my calculator, I will get an answer of 4.00 times 10 to the negative 7th meters. Accelerated honors students, you might be asked to convert meters into nanometers. To do this, you would say there are 10 to the 9th nanometers in 1 meter, which would make this answer 400 nanometers, or essentially violet colored light. Let's have a look at our second problem. Our second problem states, determine the frequency of light with a wavelength of. Remember, even though we are not provided speed of light in this problem, it is a constant that is always known. So anytime we need to use it, we can reach into our toolbox and pull this out. So in this problem, we will be using the same equation that we used in the first problem. However, this time we'll be solving for frequency. We're going to get frequency is speed of light divided by wavelength. So 3.00 times 10 to the 8th meters per second divided by, here's our wavelength, 4.257 times 10 to the 9th meters. In this problem, we will wind up with an answer of 0.0705 1 over seconds, or hertz. Notice 3 significant figures here, 3 significant figures down here. In practice problem number 3, we are going to be determining energy in joules given the frequency. Energy is our unknown, and this time our frequency is equal to 3.55 times 10 to the 17th hertz, but remember, hertz is really equal to 1 over seconds. We are going to use Planck's constant, 6.626 times 10 to the negative 34th joules times seconds. And I knew that based on this equation. This time we don't have to rearrange the equation since we're solving for energy. Solving for energy in this problem, we wind up with an answer of 2.35 times 10 to the negative 16 joules. At this point, I would like you to try problems 4 through 7 on the photons and electromagnetic radiation homework. Hi everyone. This is a short video to review problems 4, 5, 6, and 7 from the photons and electromagnetic radiation homework. Let's take a look at problem number 4. First, let's look at the question. It says, what is the frequency of a radio wave with an energy of 1.55 times 10 to the negative 24th joules? So, in this case, you're being given energy and asked about frequency. So you're going to be using the equation energy equals Planck's constant times frequency. This is the energy that is given to you. So in order to solve for frequency, you're going to have to rearrange the equation. When you rearrange the equation, you'll get frequency is equal to energy divided by Planck's constant. You can substitute in your value for frequency and energy, and you'll get frequency is equal to energy divided by Planck's constant. Here's the value for energy that's coming from the problem. Here's the constant, Planck's constant, that's down here, and we'll wind up with a frequency that is equal to 2.34 times 10 to the 9th, 1 over seconds. Notice that the unit of joules crosses out. In practice problem 5, the question says, when sodium is heated, a yellow light with an energy of 3.37 times 10 to the negative 19th joules is produced. What is the frequency of this light? And what is the wavelength? This is a two-part question. So first, we're going to have to find frequency. Once we have our answer to frequency, we're going to substitute that in order to find wavelength. So we're going to stick to this part first. If you notice, you're given the energy of the problem, so we're not going to be solving for energy. Instead, we're going to be solving for frequency. So frequency, remember, is equal to energy divided by Planck's constant. So here's our energy value. Here's Planck's constant. So when we solve for frequency, we wind up with this answer. Frequency is equal to 5.09 times 10 to the 14th, 1 over seconds. Just like the previous problem, the unit of joules will cross out. Next, we're going to take this answer and we're going to substitute it into the second part of the problem. Second part of the problem wants to know what is the wavelength. This equation relates wavelength and frequency. So we're going to solve this equation for wavelength. Wavelength is equal to speed of light divided by frequency. Wavelength is equal to the speed of light, 3 times 10 to the 8th meters per second, divided by the frequency. This answer from the previous part becomes part of the next equation. When we solve this, we wind up with a wavelength of 5.89 times 10 to the negative 7th meters. Now, for those of you in accelerated honors, you might be expected to, on a test or a quiz, convert this wavelength into nanometers. So again, 1 meter is 10 to the 9th nanometers, which is going to be 589 nanometers. So if you think about the visible light portion of the spectrum, which goes from 400 nanometers to 700 nanometers. This is red light. This is ultraviolet light. So 589 is probably somewhere in here. So it makes sense that yellow light would have a wavelength of 589 nanometers. Let's take a look at problem number 6. It says cobalt-60 is an artificial radioisotope that is produced in a nuclear reactor for use as a gamma ray source in the treatment of certain types of cancer. The wavelength of gamma radiation from a cobalt-60 source is, so this is wavelength in meters, 1.00 times 10 to the negative 12th, determine its energy. In this case, we can use that combined formula that relates energy and wavelength in a single equation. So we have energy is equal to Planck's constant times the speed of light divided by wavelength. Energy is equal to Planck's constant, this is h, times speed of light, this is c, divided by wavelength, this is wavelength down here. And we wind up in this case with an energy equal to 1.99 times 10 to the negative 13th joules. Finally, let's take a look at practice problem number 7. It says, photoelectric devices rely on the ability of light to remove electrons from the surface of some substances. The energy required to release an electron from atoms on the surface of a substance is 3.60 times 10 to the negative 19th joules. What wavelength would be necessary to cause the electrons to leave the surface of this substance? Here's a problem where we are given energy and we are looking for wavelength. So we're going to use the combined equation once again. This time, since we are looking for wavelength, we must rearrange the equation. Wavelength equals hc divided by E, h Planck's constant times speed of light divided by energy. We wind up with a wavelength of 5.52 times 10 to the negative 7th meters. That wraps up the homework on photons and electromagnetic radiation. If you have questions, please consider stopping by for office hours. Thanks very much. Have a great week.